Today, in this video, we will see fifth numerical on to find moment of resistance or to find safe UDL that the beam can carry. Numerical is the cross section of a simply supported beam of 5 meter span is as shown in the figure. If permissible stresses are 100 MPa in compression and 40 MPa in tension, find safe uniformly distributed load the beam can carry. This is I cross section of a simply supported beam with 5 meter span. Let us assume that one end is hinge or other end is roller and total span is 5 meter. And cross section of this beam is this I cross section. And permissible stresses in compression is 100 MPa. Permissible, that means this 100 MPa cannot be greater than this 100 MPa. Limit they have given us in numerical. Permissible stresses in compression sigma c is not greater than 100 MPa. That means this sigma c is equal to 100 MPa maximum. And in tension it is 40 MPa. Now we have to find safe UDL that the beam can carry this uniformly distributed load. SAFE W in kilonewton per meter. Unit of this W is in kilonewton per meter. And safe uniformly distributed load we have to find safe uniformly distributed load. Now steps for solving this numerical are: first we have to find position of neutral axis, then second moment of inertia, then we have to check safe stresses, and after this we equate bending moment with moment of resistance. Then we get this W. We will see this step by step. First step is position of neutral axis. See, this I cross section is symmetrical about y axis. This yellow color vertical line is y axis, and right side of y axis and left side of y axis both are symmetrical. But about x axis, this section is not symmetric. Again, see this horizontal x axis above this x axis this side and below x axis this side, both are not symmetrical. Top flange is width is bigger 200 mm, bottom flange width is small 120 mm. So to find position of neutral axis, formula is A1Y1. Let us consider this bottom flange as 1, wave as 2 and top flange as 3. A1Y1 plus A2Y2 plus A3Y3 divided by A1 plus A2 plus A3. A1 is area of bottom flange, 120 multiplied by 40 mm. It is 4. See this bottom flange. Area for that bottom flange is only bottom planes consider, and bottom planes is rectangle type bottom planes. So area for that bottom plane is this B into T, 120 into 40, 4800 mm. Mm square, sorry. Area unit is mm square. Now y1 is neutral axis only for that bottom plane from extreme bottom fiber. From this extreme bottom fiber to this neutral axis of bottom plane distance is this 40 is thickness by 2. 40 by 2 is equal to 20 mm is y1. Similarly, area for web A2, 40 multiplied by 200, 8000 mm square. Why this y distance is always measured from bottom extreme fiber? From bottom extreme fiber to the centroid of that portion. Now we have to consider web, so web centroid, and from bottom extreme fiber distance is this 40 plus 200 by 2, that means 40 plus 100, 140 mm. A3 for top plane is this 200 multiplied by 40, 8000 mm square. And y3 is 40 plus 200 plus 20, 260 mm. Put all these A1, A2 values in y bar equation. 4800 multiplied by 20 plus 8000 multiplied by 140 plus 8000 multiplied by 260 divided by 4800 plus 8000 plus 8000 is 158.46 mm is position of neutral axis. 158.46 mm. Now next step is to find moment of inertia. This moment of inertia is, consider this bottom plane axis is x1 axis, wave axis is x2 axis, and top plane axis is x3 axis, and neutral axis is 158.46. This x2 axis is at a distance of 140. Okay, and neutral axis is at a distance of 158.46. So first find moment of inertia for I x1 x1 axis plus I x2 axis plus top flange I x3 axis. I moment of inertia is equal to I x1 axis moment of inertia is, see this bottom flange x1 axis. Parallel to this x1 axis is this 120 mm distance. This 120 mm as it is multiply by 40 cube divided by 12. Right here 120 distance parallel to this x1 axis as it is multiply by thickness 40 cube divided by 12. This is moment of inertia for only this bottom flange rectangular portion, plus for parallel axis theorem we use this plus symbol, plus area for that bottom rectangular flange portion. 120 multiplied by 40 is area for that bottom rectangular flange portion. So 120 multiplied by 40 is 4800 is the area. Multiply by distance between this T cross section, I cross section position of neutral axis, this XX axis, and only this bottom rectangular flange x1 axis. Distance between this I cross section XX axis and bottom rectangular flange x1 axis. See this distance. This much distance. Now to calculate this distance, first consider this total distance from bottom fiber. That means this is y bar distance minus this distance minus this small distance 20 mm. So first consider this distance, and this distance is this 158.46 and minus this small distance. This small distance is 40 divided by 2, that means 20 mm. So minus 20 is 138.46 mm is this distance. (138.46) and square of this. This is parallel axis theorem to find moment of inertia about any parallel axis to this original x axis. This x1 axis is parallel to this x axis. So that's why we use parallel axis theorem in this case. Next I x2 axis for wave part. Similarly, plus this x2 axis parallel distances for wave this 40 mm. 40 as it is multiplied by this 200 cube divided by 12. Multiplied by 200 cube divided by 12. This is moment of inertia for only that wave portion, plus area of that wave portion only for that wave portion area is 40 multiplied by 200, 8000, and multiply by distance between I cross section position of neutral axis xx to only that wave part x2 x2 axis. That means this distance. And to calculate this distance, first consider this distance, xx distance, and xx distance is 158.46 mm. And minus this x2 x2 distance. This x2 x2 axis distance is, we calculate it here, this y2. So see, this distance is 158.46 mm, and minus this distance is this y2 140. So 18.46 mm we get this distance. Now square of 18.46 plus, for that top flange part, moment of inertia I x3 area, moment of inertia for that top flange part is 200 multiplied by 40 cube divided by 12 plus area for that top flange portion is 200 multiplied by 40, 8000, and multiply by distance between I cross section original neutral axis to the x3 neutral axis distance, and square of this distance. This x3 axis is at a distance from bottom fiber is 260 minus x2 axis is 260 minus 158.46 is 101.54 mm square. Now calculate this. 4800 multiplied by 138.46 square plus 120 multiplied by 40 cube divided by 12 92.66 into 10 raised to 6. This calculation is only for this first curly bracket plus next curly bracket 8000 multiplied by 18.46 square plus 40 multiplied by 200 cube divided by 12 is 29.39 into 10 raised to 6 plus third curly bracket 8000 multiplied by 101.54 square plus 200 multiplied by 40 cube divided by 12 is 83.55 into 10 raised to 6. Now add this three bracket 92.66 plus 29.39 plus 83.55 205.6 into 10 raised to 6 mm raised to 4 is moment of inertia about x axis for that I cross section. I is equal to 205.6 into 10 raised to 6 mm raised to 4. Now we have this beam is simply supported beam. So deflection of this beam is like this. This beam deflect like this. That means bottom part, on this bottom portion act tensile stresses and top portion act compressive stresses. So now see stress distribution diagram for this I section is like this. Something here neutral axis and here compressive stress and here tensile stress, and distance between neutral axis to extreme tensile fiber distance is y bar distance we have calculated in step 2, sorry in step 1, 158.46 mm. 158.46 mm. This is YT. We have to calculate this YC. So for that YC calculation, consider this full depth of this I cross section. Full depth is this 40 plus this 200 plus this 40. It means 280 mm minus this YT. This YT 150 minus 158.46. 121.54 mm is this YC. And this is we written in this step 3. Y bar is equal to YT is equal to 158.46 mm. Now we have to calculate YC. YC is equal to total distance of that I cross section beam is 40 plus 200 plus 40, 280 minus this YT 158.46. 280 minus 158.46 is 121.54 mm. This is YC and this is YT. Between YC and YC, which value is bigger? YT value is bigger. So, in step 4, check for shape stresses. To give check for shape stresses, use similar triangle equation for this stress distribution diagram. This YC upon YT is equal to sigma C upon sigma T is equal to YC upon YT. Sigma C upon sigma T is equal to YC upon YT. Let in numerical they have given us sigma C sigma T maximum values. So consider sigma T as 40 MPa, maximum sigma T 40 MPa, and from that maximum sigma T YC and YT value we have to check this sigma C value. Here yt. We have to check this sigma c value is greater than this 100 MPa or less than this 100 MPa. If this sigma c value is less than 100 MPa, that means this section is safe for stresses. And if this sigma c value is greater than this maximum allowable 100 MPa value, then this section is not safe for stresses. So check sigma t is, let sigma t is 40 MPa. Sigma c is equal to yc upon yt multiplied by sigma t. Sigma c is equal to yc is 121.54 divided by 158.46. And multiply by sigma t is 40 MPa. So this sigma c value 121.54 divided by 37.84. So 158.46 mm is yt. So calculate this 121.54 into 40 divided by 158.46. 30.68 mm is sigma c, and it is less than this 100 MPa maximum allowable compressive stress. That means this section is safe, and this sigma c unit is not mm, it is also in MPa. Therefore, okay. Now next step is to find moment of resistance. For finding moment of resistance, we have to use flexurer equation. Using flexure formula, m by I is equal to sigma by y. This m is moment of resistance, m is equal to sigma by y into I. So see, m is equal to sigma by y into I. Which sigma we consider? Because we have two sigma, we have sigma c and sigma t, and we have two y, we have yc and yt. So for this problem between sigma c and sigma t, which value we consider in this equation, and between yc and yt, which value we consider for this y. Now for that, we have to consider maximum y value between yc and yt. This yc and yt, which y is maximum? This yt is maximum. That means this 158.46 mm yt is maximum. So consider this yt for that equation. When we consider yt, then consider sigma t. So if this if this yc value is maximum, then we choose yc value, and gradually we choose sigma c value, because here both terms are similar. If we choose yc, then we choose sigma c. If we choose yt, then we choose sigma t. First check y maximum, which y is maximum, then choose y. So m is equal to which y is maximum, yt is maximum. So write here yt and write here sigma t. From yt sigma t into I. M is equal to sigma t into I upon yt. M is equal to sigma t is 40 mp, 40 into I, moment of inertia is 205.6 into 10 raised to 6. Divided by yt is 158.46 mm. So moment of resistance is equal to 40 into 205.6 into 10 raised to 6 divided by 158.46 is 51.89 into 10 raised to 6 Newton mm. Moment of resistance is 51.89 kilonewton meter. Now to find this safe uniformly distributed load, equate moment of resistance with bending moment. Moment of resistance is 51.89 and bending moment for that simply supported beam is WL square by 8. 51.89. L is 5 meter. W into 5 square divided by 8. So from this 5 square divided by 8, 3.125, 51.89 divided by 3.125, 16.60 Newton per meter is safe uniformly distributed load for that 5 meter simply supported beam I cross section beam. 60.60 kilonewton per meter. So our problem statement is to find uniformly distributed load that the beam can carry, safe uniformly distributed load that the beam can carry, and safe uniformly distributed load is 16.60 kilonewton per meter for that 5 meter simply supported beam with I cross section. Thank you very much.